Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In today's session, we are going to consider some subspaces of a matrix. You should be able now to know what a vector space is, I believe. Maybe I will go over that some other time, but we'll elaborate on that. So basically, what we want to say when we say the the subspace of the matrix rows would be what are the rows in this matrix that contain all the information, meaning if there are extra rows, they can always be written as a linear combination of these rows, whether they are all five or four of them or three of them or only two of them, it doesn't matter. These would be the independent rows in a matrix. Remember, we learned about independence when we were solving a system of linear equations using Gauss-Jordan elimination method. And we are going to apply the same exact logic here. We are going to go through the reduced through echelon form. In fact, should we use? I don't think we need to use a calculator. We can do that manually. I was going to open the matrix uh, menu, but really to work into finding the RREF of this matrix, I will go over the first column. There is the pivot of 1, and then I want to fill the rest as zeros. And since I have a -3 here, I'm going to add 3R1 to R3. Usually we write R3 plus 3R1, but I'm writing it next to R3 so everybody understands what I mean. I'm going to subtract 3R1 and I'm going to subtract 2R1, and that would lead to this matrix. The first two rows stay unchanged, 1, 3, 1, 3, 0, 1, 1, 0. But when I came to the third one, I'm going to say -3 plus 3 is 0. 0 plus 3 times 3 is 9. 6 plus 3 is 9. -1 plus 9 is 8. The fourth row, I'm going to subtract 3. So 3 minus 3 is 0. 4 minus 9 is -5. -2 minus 3 is -5. And 9 minus 9 is 0. The last row, I'm going to subtract twice the top. So 2 minus 2 is 0. 0 minus 6 is -6. -4 minus 2 is -6. And -2 minus 6 is -8. Right? I hope I did this correctly. Now I see another pivot here. So I want to get rid of everything else. So I'm going to subtract 3R2. I'm going to subtract 9R2. And I'm going to add 5R2 and 6R2, right? To fill these with zeros. For some reason, I need to check that. I think it's correct, but -6, -6, -8. Okay. Then that would lead to a new matrix that has the second row unchanged, 0, 1, 1, 0. The top row, I'm going to subtract 3. So 1 minus 0, 3 minus 3, 1 minus 3, and 3 minus 0. Here I'm going to subtract 9. So 0 minus 0, 9 minus 9, 9 minus 9, and 8 minus 0. Here I'm going to add 5. So 0, -5 plus 5, -5 plus 5, and 0 plus 0. I get a row of zeros. And here I'm going to add 6. So 0, 0, 0, and -8. So here I found another pivot. I'm going to divide by 8 to make it a 1, just to make it RREF. You know the difference, right? This is in REF. In fact, it's more. But since I have pivot in these three rows. But anyway, I'm going to say if I divide that by 8, and I'm assuming that we already divided by 8. So this row is 0, 0, 0, 1. And then what I'm going to write here is what I'm going to add or subtract from the new matrix, not for this one. What I mean is that I'm going to subtract 3 R3, but it's a new R3. I'm going to subtract 3 times that. Instead of saying write this another time or saying subtract 3/8 of row 3. It doesn't make sense, right? Here there is nothing, here there is nothing. Here I'm going to add R3, but new R3. So when I subtract 3, I will get 1, 0, -2, 0, because I'm going to say 3 minus 3. Okay? The second one stays the same. The third one is here. The fourth is zeros. And the fifth would be zeros when I add these two. But this time I'm going to add the old R3. So 0, 0, 0, 8 minus 8 is 0. I get 2 rows of 0, which means these 2 rows can be written as a linear combination of the other 3. I only have 3 rows that contain everything I need to know about this matrix. So I'm going to say a basis for the row of A is, I'm going to write it as a column just because I don't have enough space. Usually we can say, so I will go to the original. Notice they were the first 3 rows. So I'm going to write the 3 rows, 1, 3, 1, 3, comma, 0, 1, 1, 0, comma, -3, 0, 6, -1. And I'm saying that these 2 rows can be written as a linear combination of the first 3. Uh, I can't say it from the top of my head, but uh, let me see if I can. Hmm. Yeah. If you multiply the top by 3 and then subtract 5 times the second, so 3 times 1 is 3, minus 0 is 3. 3 times 3 is 9, minus 5 times 1 is 4. 3 times 3 is 3 times 1 is 3, minus 5 is -2, and 3 times 3 is 9, minus 0 is 9. And you can also find another relation to get me this one. Maybe it's not, I don't know if I can find it from the top of my head. Uh, Probably not. That has to be, no, I really don't know. If I multiply this by 3 and subtract, let's see. No, that has to be times 2 since this is a 2 and this, no, not necessarily. The 1 minus -3 is 2. And when I multiply that by -3, it would be 3 minus 3 plus 0 is 0. 3 minus 1 is 2. Minus 6 is -4. 3 times 3 is 9. Minus 0 plus 3 times 0 or whatever is 0 is still 9. I don't know. You can easily find it if you write some equations in some unknown. So you can say if I multiply this row by C1, this by C2, this by C3, and equate that to 2, 0, -4, -2, a calculator can give you the values of C1, C2, C3 that would make that. But that's not our issue now. Our issue is to say if this is the basis for the row of A, I can think that also I can find the basis for the columns of A. And that would be, notice, here are the pivots. First column, second column, and fourth column. So they would be 1, 0, -3, -3, 3, and 2, and the second column 3, 1, 0, 4, 0, and then the last column 3, 0, -1, 9, -2. So I see that, notice, this matrix was a 4 by 5. The row space of A lives in R4. It has a vector made of 4 entries, so it lives in M, or M, where M, this is matrix R, M times N. So the basis of row of A lives really in Rn, which is R4, the number of columns. And the basis for the column of A lives in Rm, which is 5, the number of rows. So it's like backwards. I have 4 rows, so my rows lives in R. I have 5 rows, so R lives in R4, and I have 4 columns, so the columns live in R5. So these two, notice that the dimension of the row of A is 3. I have 3 vectors, as well as the dimension of column of A. They have to match, right? Because I'm looking at the pivots. I have 3 pivots, meaning 3 rows, and also 3 columns. The rows are 1, 2, 3. The columns are 1, 2, 4. So the number, so here we say the dimension of R of A, or row of A, equals that of the column of A. In this case, it's 3, and 3 here would be called the rank of matrix A. Remember the word rank? What is the rank? In loosely speaking, the rank of a matrix is the maximum square size of the matrix that can be inverted, meaning its determinant is not 0. So in this case, I have 4 by 5. I can make a 4 by 4 matrix, right? I can take these 4 by 4, or these 4 by, these 4 by 4, or those 4 by 4, or first, second, fourth, and fifth, or second, first, third, fourth. You can make some linear combinations, but none of those will have an inverse. The determinants of all 4 possible 4 by 4 matrices will have a determinant of 0, meaning they are singular matrices. They don't have inverse. However, the maximum matrix that has an inverse that I can make out of this 4 by, I keep saying 4 by 5, I'm sorry, 5 by 4 matrix is a 3 by 3. I can have a 1 by 1, of course, I can have 2 by 2, and I can have 3 by 3, but no more. That's the meaning of the word rank. So we found 2 subspaces of Rm and Rn, which are called the bases for row, the subspace row of A and column of A. There is one last one we can find from this matrix. It's called the null of A. Null of A. And the null of A is the solution to AX equals 0. Meaning, if I take this matrix and write it, we will end up with that, right? So if I multiply this matrix 1, 0, -2, 0, 0, 1, 1, 0, 0, 0, 0, 0, I'm sorry, 0, 0, 0, 1, 0, 0, 0, 0, times 4x's, x1, x2, x3, x4, I will get 4 zeros. Wait a second. I know because I have a pivot here, a pivot there, and a pivot at the end. It means these are basic variables. These variables are very important. I cannot take them away. But this column is a free variable. Remember, we said the rank is 3, so I can only have 3 important columns. The fourth is not important because, again, I can make it as a multiple combination or linear combination of columns 1, 2, and 4. So how do I solve? I'm going to call it T. Okay. And then I'm going to say the first, if I say here x1 for the column 1, x2 for the column 2, x4 for column 4, and t for the column 3, then it says x1 plus 0 minus 2t plus 0 equals 0. And then if I want to write an equation here, I'm going to say x2 plus t equals 0. And then for the last one, I can say x4 equals 0. T can be anything. Of course, it can be a trivial solution, t equals 0, but that doesn't help. But if I say t is any number in the world, I can write x1 as 2t and x2 as negative t, and x4 is 0. And x3, of course, is t. So I did say that the null space of A is the span of what? 2 t times 2, negative 1, 1, 0. Meaning, if I pick any value of t, and I'm going to multiply these by the values of x1, x2, t, and x4, I will always get 0. That's why we call it. And of course, a basis for the null of A is simply this vector 2, negative 1, 1, 0. So the dimension of the null of A is just one vector. There I had 3 for the row and the column, and they were equal, and we call that the rank. Here, it's only 1, and we call it the nullity of A. So the dimension of the null of A is called the nullity of A. And it's always going to be the case that the rank of A plus the nullity of A equals n, where n is the number of columns, right? We said m times n. So n is the number of columns. I had 4 columns. 3 of them, 1, 2, and 4, were basis for the row or the column, meaning that's the rank. So the nullity would be 4 minus 3 equals 1. Not only that, there is something important. If I say that the null of A is perpendicular to the row of A. What? Yeah, remember when we said 2 vectors are perpendicular if neither of them is 0, and these are not 0 vectors, if and only if. What? Yes, their dot product equals 0. So let's see, here is the nullity and here is R. Notice they have the same size because both live in Rn, 4. 2 times 1 is 2, minus 3 is negative 1, plus 1 is 0, plus 0 is 0. 0, negative 1, plus 1 is 0, plus 0 is 0. Negative 6 minus 0 plus 6 plus 0 is 0. So yes, the null is perpendicular to the R of A. Wait a second, we said we are going to look at 4 subspaces. What else is there in the matrix? You found rows, we found columns, we found null, nothing else. Yeah, there is nothing else. But you said there is something else. It's called the left null space of A. We call it the left because we are going to take the transpose of A. Here is the A transpose. 1, 3, 1, 3, 0, 1, 1, 0, negative 3, 0, 6, negative 1, 3, 4, negative 2, 9, and 2, 0, negative 4, negative 2. In fact, you know what I'm going to do? Let's see if I have. Do we have? No. Okay, so let's do the RREF. So we are going to solve A transpose X equals 0 and find the null of A transpose. Meaning I'm gonna augment it with 4 zeros, so I will have 4 rows and 6 columns. So let's create a matrix that is 4 by 6 and enter these numbers. Let's see if we can do that quickly. 0, and then 3, 1, 0, 4, 0, 0, and then 1, 1, 6, negative 2, negative 4, 0, and 3, 0, negative 1, 9, negative 2, 0. And then I just don't want to waste your time. I'm going to go to matrix. Oops. A. Okay. I end up with that RREF. Forget about the last column. This is just the augmented matrix. So I get 1, 0, 0, 3, negative 1, 0, 1, 0, negative 5, 3, 0, 0, 1, 0, negative 1, 0, 0, 0, 0, 0. You can see that the row of A sub t is 3 and it lives in R5. In fact, look at that. Look at those. The first row, the second row, in fact, and the fourth row, in this case, not the third, because they moved the 0 down. But you can see the first row was the first column here, is the same, and the second is the second, and the fourth is the third here. The row of the complement is the complement. Okay. I'm sorry, I meant the row the row of the transpose matrix is the column of the original matrix, and the columns, the first, second, and third are 1, 3, 1, 3, 0, 1, 1, 0, and negative 3, 0, 6, and negative 1. So the rows of the matrix are the column is the column space of the transpose, and the column of a matrix is the row space of its transpose. So we haven't solved for the null of the A transpose, which we call the left null space. So the null of A transpose is Notice I have 5 columns, x1, x2, x3, but these two we are going to call them S and T. Notice we usually say T for parameter. If you have 2 parameters, we use the previous letter, which is S. If we have a third one, we go to the previous letter, which is R, and that's basic, excuse me. So like we did here, we can say it's the span of S times something and T times something. And then the basis would be these two vectors. Okay, look at the S. X minus plus 3s equals 0, so x equals negative 3s. x2 minus 5s equals 0, so x2 is 5s. x3 doesn't have s, so it's 0. S is s, and t has nothing to do with s. How about the t? x1 minus t, so x1 is t. x2 plus 3t, so it's negative 3t. x3 minus t, so it's t. x4 is s, doesn't have a t, and the t is just 1t. Meaning, the basis for the left null of A are these two vectors. Again, the rank of the A sub t is 3, like the original matrix, of course, but the matrix has 5 columns. That's why its nullity is 2, not 1 like previously. But you know what? The nullity of A transpose is perpendicular to the column of A. Notice there are 5 vector that lives in Rm, which is 5, like the columns. We have 3 columns here that if I multiply, like let's multiply, say this and that, you get negative 3 plus 0 is negative 3 plus 0 is negative 3 plus 3 is 0 plus 0 is 0. So this one works with that. Negative 9 plus 5 is negative 4, 0, plus 4 is 0, 0. So it works with that. Negative 9 plus 0 plus 0 plus 9 plus 0 is 0. How about this guy? 1 plus 0 minus 3 is negative 2 plus 0 plus 2 is 0. How about the second one? 3 minus 3 is 0 plus 0 plus 0 plus 0. 3 plus 0 is 3, plus negative 1 is 2, plus 0 is 2, minus 2 is 0. So what we found so far is the basis of row of A or column of A, which are equal, they always equal the rank of the matrix. And the nullity of the matrix is n minus that minus the rank, meaning the rank plus the nullity always equal n, where n is the number of columns of a matrix. We also said that the row of A is perpendicular to the null of A. So if this is the basis for the null of A, and these are the rows, the dot product of these two vectors, or these two vectors, or these two vectors will always give you 0, meaning they are perpendicular. And we said that also, I don't need to calculate the row and the column of the transpose of A, because the row of A is the column of its transpose, and the space for the column of A is the space of the row of its transpose. But what's important is the null of A transpose, because these two vectors are perpendicular to the column of A. So now we learn about 4 subspaces: the row of A, the column of A, the nullity or the null of A, and the null of A transpose, which is called the left null space of A. And we found the relationship between them. And that's pretty much everything I wanted to go over today about these 4 subspaces, because we are going to build on that later on. Thank you very much for your time. I hope it wasn't that dry session. Thank you very much for watching. If you have any questions, please feel free to drop a line for me and I will get back to you as soon as I can. Otherwise, thanks again and hope to see you soon.